In this lesson, we'll try to consider the theorem of three forces in equilibrium and try to prove it using the axioms. The theorem says if three forces keep a body in equilibrium and two of them meet at a point, then the third force must also pass through that point and all the three forces must be coplanar. We'll try to prove this theorem using the two axioms. That is, one axiom is parallelogram law, and two forces in equilibrium law. Okay, this parallelogram law gives us how to find resultant of two forces which are meeting at a point and the two forces in equilibrium. It says that two forces can be in equilibrium only when they are equal in magnitude, opposite in direction, and are collinear. In using these two axioms and trying to prove, we use a particular method of proof which is called reductio ad absurdum. Okay, or it is called argumentum absurdum. Argumentum ad absurdum. Okay, this word reductio ad absurdum means reduction to absurdity. Argumentum ad absurdum means argument to absurdity. So what we try to do in this way of proof is that we'll assume that to begin with this theorem is incorrect. Okay, and then by using axioms we'll try to come across a situation where one of the axioms is violated. Okay, since no axiom is violated, the assumption that the theorem is wrong is incorrect. That is the kind of line of proof we use. So to begin with, let us consider that we have three forces P, Q and S. Let us say this is force P. Okay, and you have another force Q which is intersecting P. So you have two forces meeting at a point, okay, which is permitted in the theorem. Two forces meet at a point and the third force will take it in such a way that this theorem is violated. This theorem says if these three forces keep a body in equilibrium and two of them meet, P and Q meet, the third force, let us say the third force is S, S must pass through the point. It must pass through that point, which we will violate. So we will take the force S to be somewhere like this here. Okay, and then say that the forces P, Q and S, they keep a body in equilibrium, which is against the theorem. And see what happens when we try to simplify the situation. The first thing we'll try to do is we'll try to find the resultant of these two forces P and Q. You draw a line parallel to the line of action of P, and then you will draw a line parallel to line of action of Q to meet at a point, and we draw a line along the diagonal. I'm drawing a thick line just to indicate that it is a resultant and mark it as R. We can make a couple of observations here. Because P and Q are two straight lines, we can always consider a plane passing through them, because a plane passes through any set of two straight lines. So you'll have a plane passing through a plane which contains P and Q, lines of actions of P and Q. Because you have parallelogram construction, okay, this R also is contained in the same plane. Once we find the resultant R, we know that the resultant produces the same effect as the forces P and Q. So if P, Q together with S, okay, all the three forces are keeping a body in equilibrium, then R and S will also have to keep the body in equilibrium by definition. Okay, once we note this definition, we can get rid of these forces P and Q, okay, and just retain R. Okay, so now you have R and S, two forces that are keeping a body in equilibrium. That is what is our original assumption. Our original assumption says that forces P and Q meet at a point, and a third force S, which is not passing through that point and not contained in the plane, keeps a body in equilibrium. So that would amount to having R and S keep a body in equilibrium. But we know from the axiom that if two forces keep a body in equilibrium, let us say forces X and force Y, the requirement specified is that magnitude of X must be equal to magnitude of Y. They both must be oppositely directed and collinear. This axiom is violated here. Okay, but violating an axiom is not permitted. So the only thing that we can conclude is that our original assumption that P and Q, they do not meet at a point. Okay, this P and Q meet at a point and S does not pass through is incorrect. So S also in some sense must pass through this point. You should have S acting somewhat here. So this direction of S is incorrect, this direction of S is incorrect, and S also passes through this point. Okay, this is a very important theorem which we'll be using in many situations. In subsequent classes, we'll try to consider a couple of such theorems and try to prove them, and then try to work a few problems.